right. Pencils go down and colored pens come up, but today's warm-up is quite a bit different. I don't even have an answer up here to reveal because there are infinite possibilities. We've got 21 people in the room at the moment. There's probably going to be 21 different stories. So let's see what your story was. Got 3 volunteers, and then I'll call around for some others. We'll start with Amir, Cheyenne, Gary, and Tristan. Go.
Fleming kicked a soccer ball, and it increased in distance from the ground rapidly, then bounced 4 times before coming to a stop.
Okay.
A basketball is thrown sharply and escalates high, then drops sharply. It bounces up and down steadily until it reaches a complete stop.
Excellent.
Jose is playing with a super bouncy ball. He throws it at the floor, making it bounce extra high, but it hits carpet on its second bounce, and it begins to bounce much more slowly than the rest. That's it stops.
Excellent. Tristan?
I'll kick the football from the ground. Football moves quickly and gradually increases until it stops, and gradually increases and increases quickly 3 times before it stops.
Very nicely done. Very nicely done. I've done this with 3 classes, and by far those are the best descriptions, the best support for your story that I've heard. So far I've heard tons of great themes, but a lot of students were struggling with how to incorporate the picture into the story, and so far all 4 people have done that. Every single person talked about the fact that the ball had to go way up, or whatever object you were talking about went way up, came down, and then went up again, but not as high as the first time, and then gradually got lower and lower until it came to a complete stop. I love how people included coming to a complete stop. Great job. Anyone have another one that they would like to share? So far today I've had airplanes, I've had kangaroos, I've had basketballs, footballs, Super Balls. I've had pretty much a huge variety of different themes, and they are all appropriate. Does anyone have one that they're not sure of that they would like to share, that they would like to get feedback on? Good, well, we're doing well so far. Any comments or questions? Okay, so last time we were together, we began chapter 3. And we spoke about graphs in very general terms. In fact, we looked at graphs, like you saw during the warm-up, that didn't even have numbers on them. And so we were trying to lay the foundation for where we were going. Today we're going to become much more specific. And it's a lot to take in. Also, this entire year has been one long building process. We started at the beginning of the year and built to where we are now. Today's lesson is also going to be a mini building process. We're going to start at the beginning of the lesson exploring the idea of relations, and then we're going to build on it until we finish with the idea of a function. So, what is it that I'm talking about? Well, you already know what a relation is. You may not have heard the term, but you saw it last time. It's a relationship that can be shown by a graph, but can also be shown by a set of ordered pairs. Now, I am operating as if you know what an ordered pair is. So everything we do today is based on the idea of ordered pair. If you don't know what an ordered pair is, I'm going to be talking a little bit about the basics. But if you're confused, you need to rely on your teammates quietly, but you need to actually talk and engage them and say, okay, what is he talking about? I don't understand. What's the X? What's the Y? You need to speak up. While I'm in the middle of demonstration, I'm not going to be able to address your individual needs. During a checkpoint, if you're still lost, you raise your hand and then I can come to you and work with you individually. Does anyone have any questions about that? So, ordered pairs is a key element. So, here's an example of a relation. You already read this, but let me go over with you. If you've never been a part of a track meet or know of track meets, then this may be new for you, but this is legitimately how this works. When you come in first place, you get a certain number of points. Second place, third place, fourth place. A track meet is a team event, so every event gets a certain number of points, and then the team with the most points wins. Okay? So at least if you get fourth place or above, you're going to get points. This scoring system is a relation. There's a relationship between the place you come in and the number of points you earn. It can be demonstrated or shown by a set of ordered pairs. So now here is the set of ordered pairs from this scoring system. First place gets you 5 points, 1, 5. Second place gets you 3 points, 2, 3, and so on and so on. If you're not looking up here, you're going to miss the next part, which is this symbol right here. I will often say the squiggly bracket. I believe its technical term is a brace, but I like to just call it a squiggly bracket. And it's going to take you a little getting used to draw it, but that open brace and this one at the end denotes a set. That says that this is a set. So what we've done here is written the relation as a set of ordered pairs. We can also write a relation in other ways. We can write it as a table, a graph, or a mapping diagram. And you're going to learn all of these today. Any comments or questions so far? So we are going to build from what we know about relations to tables, graphs, and mapping diagrams. After we establish those concepts, then we will move on to domain and range. You should have been introduced to domain and range last year, but if you weren't, you will understand it this year. The domain is the set of x values. The range is the set of y values. The domain of the track meet system is all the x values written as a set. So if we take the 1, the 2, the 3, and the 4, and make a set out of them, that's called the domain. Then if we take the 5, the 3, the 2, and the 1, and make a set out of them, that's all the y values, that's called the range. So we go from relation to establishing different ways of writing a relation, to establishing what a domain and range is, and from that, we get the final idea, which is a function. And a function is a special type of relation. The statement that defines it is confusing. Each domain value is paired with exactly one range value. Even to this day, I still find that very confusing. But later on, when we get to the idea of function, I'm going to explain it in a way that I believe you will understand. So don't worry so much about the technical definition. Pay attention when we go over it later on. Okay? Are there any comments about the overview? So as I said, it's a mini building process. Let's go to the beginning. And I establish the different ways of representing a relation. So you have a ruler at your desk, and you're going to need the ruler. I'm also going to be handing out grids for you to use. And the grid slip that I'm giving you is double-sided so that you will have extra grids to use. The stapler is still being passed around, so you will staple this into your work at some point. It doesn't have to be right now. Nor do we need to fight about the stapler or worry about where the stapler is. It's not a big deal. If you're worried about the stapler, then you're not worried about what we're doing. So, you have a ruler to use. Those were already out. Now you have grids to use. You're going to need both. So, example 1. We're going to take a relation and turn it into a table. Then we're going to turn it into a graph, and then we're going to turn it into a mapping diagram. Here is the relation, right here. Of course, you have this already written down. So, I said at the beginning of the lesson that the entire idea was based on the concept of an ordered pair. So let's start with that so that we can make sure we're clear on what I'm talking about. So, let me get rid of this for a moment. And this. And let's just focus on 2, 3. What does it mean? What is it? How do I read that? What is its purpose? Could it be 3, 2? Can I take the 3 and put it on top of the 2? Can I put the 2 underneath the 3 or vice versa? What is the purpose? Let's start with Amir, Gary, and Tristan. Yes?
2 represents the x-axis and 3 represents the y-axis.
Okay, Gary, and what were you going to say?
Same as he said, because the x always comes first.
Okay. Tristan? Okay, so the 2 represents where we go on the x-axis, and the 3 represents where we go on the y-axis. Exactly. And so the whole idea that we're going to be exploring today is based on that. So let me back up a little bit. So now we have all of this. So we have an x, a y, x, y, x, y. So first we're going to put it into a table. Now, I have a computer to help me make these perfect, beautiful tables. You don't need to make a table like this. You need to make what's called a t-table. And it's very simply a lowercase t, but bigger. So all you need to do is this. You need a horizontal line going across right here, and a vertical line going straight down the middle, starting above it and going below it. That is a t-table. That's all you need, and you have a ruler to help you along if necessary. The left column represents the x's, and the right column represents the y's. Take the x's and put them down. Take the y's and put them in the right column. So 2 goes with the 3, 4 goes with the 7, 6 goes with the 8. It's pretty basic. So everything is matched up. I had some extra rows just in case I needed it, but I do not. Any questions about how to construct a table? Now, no questions? So now a second representation is a graph. So now I've given you grids, so let's go to the first grid on your slip. It doesn't matter which one, really. And I've given you a blank grid almost exactly like the one I have here. And we need to put these ordered pairs on the grid. So the x-axis starts at 0, and the grid is pretty small, so I'm going to go every 2. So that's going to be a 1, 2, 3, and so on. And then this starts at 0, and I'm going to go every 2 again. So we've laid out our axes, and now we plot the points. Give me a thumbs up if you remember how to actually plot points on a grid, and it's okay if you don't. Okay, so let's do it at the same time. You go ahead and do it, and I'm going to go ahead and do it. So 2, 3. I go over 2, up 3, plot the point. Make a nice clear dot on the graph. 4, 7. 4, and then go up to the 7. Put a nice clear dot on the grid. And 6, 8. And you should have a graph that pretty much looks exactly like mine because your grid is just like mine. Now, why do we need the different representations? Well, this representation is nice and organized, and it shows us that they're ordered pairs. This representation is nice and organized. We can see the ordered pairs. We can also see a list of the x's and a list of the y's. But the graph is incredibly important because watch this. I do not want you to do this. I just want you to watch. If I connect the dots, watch what happens. And this relates directly to what we did last time. Now it tells a story. Whereas if I look at this, it is nearly impossible to see a story. And if I look at this, it's nearly impossible to see a story. But if I look at this, and if I'm looking at it correctly and appropriately, now I can see a story. And so the graph is incredibly important. Incredibly important. But I'm not sure if we're supposed to connect the lines in this graph, so I'm not going to. I don't know if this is continuous or discrete. Does anyone have any comments or questions? Any concerns about the graph? All right, so the last idea is called a mapping diagram. And what you need to do is draw 2 rectangles next to each other. The one on the left is the x's, the one on the right is the y's. The mapping diagram is another way of representing the relation, but it has a benefit that the other representations don't have. And you're going to see the benefit a little bit later. But let's just learn how to do it. It's almost the same as the table. So it's actually going to look just like the table. 2, 4, 6, and then 3, 7, 8. So we've got 2, 4, 6, and then 3, 7, 8. But the difference is that we are going to draw an arrow from the x to its partner y. So we are literally going to draw an arrow, start all the way on the left, inside the rectangle, and draw it straight inside the other rectangle to its partner. It's map. The 4 gets mapped with the 7. And the 6 gets mapped with the 8. Now this mapping diagram doesn't look a lot different than the table. But you're going to see diagrams later on where it has arrows going like this, or arrows going like this. And there's going to be a benefit later on. Right now, I'm just having you learn how to draw a mapping diagram. So, does anyone have any comments or questions about mapping diagram? Go ahead.
For this mapping diagram, it's just like plotting points on the grid. So, what if they give you a set of pair numbers? Well, not really a set of pairs, but like a real life application. You have to apply that to what you're doing. Like, say, it's going to be 2 and 6, but the 6 is all the way down here and 2 is up there. Is that when the arrows come in?
Yes, and you're going to see that a little bit later. Okay, good. Any comments or questions about any of these representations? Anything at all? Okay. Checkpoint number 1, let's see if you've learned it. We only did one question together, but it seems like you guys understood. So, express this relation first as a table, then as a graph, then as a mapping diagram. So you have 3 things to draw. Give you a little over a minute per. So it's going to be 4 minutes. If you have any comments or questions, anything at all, please just let me know and I will come to you and work with you.
Mr. Gall, for the graph part, do you
One
use a
second.
paper?
Yeah, use the slip. Yeah, absolutely. Okay, so this checkpoint is not really conducive to calling on volunteers, so you just check your work. Here is the table. Here is the graph. And here is the mapping diagram. I had a student in another class who pointed out that this looked like it was negatives, like -1, -2. That's not the case. The publisher, for some reason, put the 1 on the right instead of over here. That's really just saying 1. So, not sure why the publisher did that, but that's what they did. So, give me a thumbs up if you got all 3 of them. Good, put your thumbs down. Are there any comments or questions? This type of graph has a name. What is its type? Yasmin? That is called discrete. This graph, during today's warm-up, that type has a name. What is its name, Adriana? That is called continuous. We are now going to build to the idea of domain and range. And there's two different ways to write domain and range. And it depends on whether the graph is discrete or continuous. So remember that the domain is all the x values, the range is all the y values. So, with that in mind, example 2. Unfortunately, we do need this picture, so what I would like you to do is use one of your grids, and as I said, it's double-sided, to make this picture because we're going to do something with it. So it should just take you 30 seconds or so. You could write above it example 2a so you remember what it goes with. And in example 2a, we're asked to give the domain and range of the relation. So, when we're asked to give the domain and range, we want to actually be able to write domain, and then write what it is, and we want to be able to write range, and write what it is. The domain means all the x values that are being used in the graph. So we are only concerned with x values that have something to do with this right here. In other words, we don't care about the x values over here, we don't care about the x values over here, and we don't care about any x values over here. We only care about the x values right here. So how do you find those x values? So I have a technique for you, and it works really well. You have a ruler. You have a ruler. And so what you're going to do is you're going to hold the ruler so that the edge of it is going straight through that first point. And you are going to use your pencil, and you are going to draw a light dotted line going through the point all the way through the x-axis, like that. And drawing a dotted line is simple. Just put your pencil down and pick it up, and put it down and pick it up as you move it along, and it will just magically create a little dotted line. It doesn't need to be dark. It needs to be just a nice light dotted line. Now move your ruler over so the edge of it is passing through the middle of this point. And again, holding it straight, draw a nice dotted line going straight through all the way through the x-axis. Now the grid is not filled in, but this is a 1, and this is a 5. And so what that means is we are using the x-axis from here to here. That's the only part of the x-axis we are using, from here to here. That is the domain. The part of the x-axis that we are using. So now we have to figure out how do we write that here. Since this is continuous, if I tried to write this, I would have to write 1.0000001, 1.0000002, 1.0000003, 1.00004, and then I would have to keep going and going and going until I had 1.1, then 1.11, then 1.12, and I would have to keep going and going and going, right? That's how I would write down every number from here to here. But there's a much better way. That would be ridiculous to try and list all those numbers. I would be here forever. It's not practical. But you learned another way to write it last chapter. It's called a compound inequality. And so what we say is all of the numbers between the smallest number and the biggest number, 1 and 5. And if you think about it, this makes perfect sense, because if I take this and put it down here, it matches almost perfectly. So that's what we're doing, is we're saying we're using all the x values between 1 and 5 and including 1 and 5. It's including 1 and 5, and that's why we put the bars underneath. If it wasn't including 1 and 5, then we wouldn't. Any questions about how we did that? Caleb?
Okay, wouldn't it be like greater than or equal? Never mind.
Okay, it does. It is a little confusing. There's no doubt about it. But let's forge on and let's look at range. Range is all the y values. And so we want to be able to write out what part of the y-axis is being used. Is this part of the y-axis being used for this graph? No, the graph doesn't go up there. Is this part of the y-axis being used for the graph? No, the graph doesn't go down there. So the question is, what part of the y-axis is the graph using? So if we use the exact same technique, but going horizontally, we will be able to see the range. And so what I want you to do is take your ruler and hold it so that the edge is passing through the middle of that point again, but now going horizontally, and draw a dotted line going through the y-axis. Then move your ruler down so that you can draw a dotted line going through here. And so you can see that this line passes through the 4. There's nothing written here, but we know that that's a 3. And so we can see that the bottom of the graph is at 3 and the top is at 4. If we use the exact same notation, but instead of an x, we use a y, and put the smallest number to the left and the biggest number to the right, now we have the range written out. We use this style of notation when the graph is continuous. If the graph is discrete, we will use a different style of notation. Are there any questions or comments? So that was example 2a. Let's look at example 2b, still working on finding the domain and range. Give the domain and range of this relation. So go ahead and sketch the relation quickly. Just draw a quick little rectangle, put in the numbers and draw the arrows. And then we want to identify the domain and range. The good news is that we've done the challenging one. These are much easier. The domain and range are given to us. We just have to write them in the right way, in the right order. When we have a discrete situation, this is discrete because we have specific points. We use set notation, which means the squiggly bracket. So write an open squiggly bracket, and then put all the x's from smallest to biggest. 1, 2, 5, 6, close squiggly bracket, and that is the domain. The range is going to be written the same way, open squiggly bracket, and put the range in order from smallest to biggest. -4, -4, -1, and 0. Close squiggly bracket. And that is domain and range when you have a discrete situation. This is discrete because it's just a set of specific points. This was continuous because we had 2 points, but then they were connected together. That's continuous. Any comments or questions about this one? Amir? You sure?
Yeah.
Any other comments? Go ahead.
I was wondering, like, 'cause in my paper I put it from biggest to smallest.
Smallest to biggest.
Yeah.
Smallest to biggest. Any comments? Now, there is a part C for this example, but I don't want you to copy it. I just want you to look. So put your pencils down for 1 minute. But you have 2 options. Your pencil's on your desk, and you're looking up here, or you're not looking up here, but then you're copying. Those are your 2 choices. Here you go. So give the domain and range. Now we have it in the table view. So I want to write the domain and range. Domain, range. It's listed for me. That's the domain and that's the range. So it's no different than a mapping diagram. 1, 4, 8, smallest to biggest. But now look at the range. What do you notice? Something's different. Chanel? There are 2 1s. And so you do not write it twice. You write it 1 time. 1 and then a 4. So that was the only point of this example, was to illustrate that if the same number shows up more than once, you only write it once. Does anyone have any questions about that? Tristan and then Chanel? Yes, it is.
When, I mean, it probably sounds stupid, but why don't you write it as like, wait, I don't know where it was in it, but anyway, why don't you write it as like 2y?
You mean because there's 2 of them?
Yeah.
I understand what you're saying. It just doesn't really apply to this situation. When you talk about domain and range, we're talking about a range of numbers or a set of numbers. So I understand your point, but it's not really, it's not applicable to this situation. All right, so let's see how we do on our own. Give me the domain and range of this. You got 2 minutes. Remember, for checkpoints, you don't have to copy anything unless you need to. got 1 minute to team talk. Compare your answers to the teammates, to your teammates, and see if you guys have the same answer. If not, discuss. Go. Yeah, you're gonna have to show your paper or.
Did you get the same thing that someone said? Would you put the range? I put y is greater than equal
All right, give me a thumbs up if you and your team agreed on the domain and range. You got 1 team, 2, 3, 4, 5, 6, 7 teams. Put your thumbs down. So let's see if your team got it right. The domain is that, and the range is that. Are there any questions? Any concerns? Are we sure? Because the next idea comes from this. Okay? So, now the final idea. What we've been building to is this idea of something called a function. And again, I said earlier that the technical definition, I think, kind of, it's strange and it's hard to understand, and I still don't get it. But once I explain it to you in a different way, I think it will make sense to you. A function is a machine. That's what a function is. It's a type of machine. And that's what you're going to think of every time you hear the word function. You're going to think of a machine. So we are going to use an example. And we are going to do the example, but I'm going to pause partway through it to do a small little activity. So, let's get set up. Start example 3a. And we're asked to give the domain and range of the relation, but then we're also asked to tell whether it is a function. That's the part that we don't know yet. And here is the relation. Now, you don't know how to determine whether or not something's a function, or maybe you do, but I haven't worked with you yet on it. So we don't know how to do it yet, but I'm going to tell you the best way to approach it at the beginning is to turn the set into a mapping diagram. The mapping diagram reveals whether it's a function or not instantly. So we're going to draw a mapping diagram. And so we need 2 rectangles next to each other. And we take the domain and list it down the left rectangle. But let's look at the domain before we do it, because we want to list it from smallest to biggest. So we've got 3, 5, 4, and a 3 again. We don't write the 3 twice. So now take those numbers and list them from smallest to biggest. We've got 3, 4, and 5. Now the range. We've got -2, -1, 0, and 1. They're all different. Let's list them from smallest to biggest. -2, -1, 0, and 1. Now do the map. The map is the arrows, and that's the critical piece. So the 3 gets mapped to, excuse me, wrong direction. The 3 gets mapped to the -2. The 5 gets mapped to the -1. The 4 gets mapped to the 0. And the 3 gets mapped to the 1. That's a mapping diagram. Now I want to pause and talk about the idea of a function. So we could already do the domain and the range, but we don't know whether this is a function. So let's pause this for a moment. I'm just going to pause this for a moment. And I would like everyone to pick up your calculator. And make sure you follow along with me, and what I ask you to do, you do. You don't have a calculator? I'm sorry about that. Look on with the person next to you. So, I would like to do an input. An input is what we put into the calculator to get something out of it. The first input we're going to put in, and I'm going to keep track of it up here on my whiteboard, is 2 times 5. I would like everyone to punch into their calculator 2 times 5 and push the equal button. Do that? No, you already did. What is the result on your calculator right now? Raise your hand and wait to be called on. Isabella? I'm sorry? 10. So you should have a 10 in your calculator right now. Give me a thumbs up if you have a 10. Good. Clear your calculator. I would like you to think of another expression. This is an expression. I would like you to think of another expression that we could punch into the calculator, any expression at all that we could punch into the calculator, that the result would come out to 10. Give me a thumbs up when you've got it. Just put it in your head. Give me a thumbs up. I should see a thumb up for every single person because every single person should have an expression. If you're not sure, you'll understand in a moment. Jesse. 1 times 10. Chanel. 3 plus 4 plus 3. 1 times 10. Keep your thumbs up so I know who's got one. Adriana. 11 minus 1. Amir. Good.
What?
3 divided by 3. Oh, 30 divided by 3. I thought Yadesh. I'm sorry? 100 divided by 10. Good. So let's go with 100 divided by 10. So everyone punch in your calculator 100 divided by 10 and confirm that we get a 10. So we've done 2 expressions, we've done 2 inputs. These are the inputs, and these are the outputs. I want to save space, so I'm going to write it like this. Anyone have a problem with me doing that? Is that still clear? 2 times 5 is 10, 100 divided by 10 is 10. Any questions about that? So now someone answer this question. Is your calculator working or is it broken? Raise your hand and answer my question. Is your calculator working or is it broken? Caleb? It's working. Gary, is yours working or broken? It's working. And And we have evidence of it right here. This is working because we put an input in and we got an output. We put a different input in, even though we got the same output. This is considered working. What's another word for working? Functioning. This is functioning, right? Now the next part's going to require a little imagination. So now I would like you to clear your calculator, and I would like to do 6 times 3 and hit the equal sign. 6 times 3 and the equal sign. What is the result? What's the output of your calculator, Marcus? 18. Now the next part requires imagination. Because I'm pretty sure all of your calculators are working, it's hard for me to demonstrate what it looks like when it's broken. So now we have to use our imagination. So now I want you to pretend for a moment that your calculator is broken, and I'll demonstrate. So now mine's broken, and I punch in 6 times 3. I punch the same one again. 6 times 3. I hit the equal sign, but, oh, this time it says 25. Huh. Now, before I analyze my machine, I want to save space. So I'm going to rewrite. So we've got 6 times 3 equals 18. 6 times 3 equals 25, but I want to save space, so I'm going to do this. It's the same thing, right? It said equals 18, and it said it again, and it said equals 18, but now I've saved space, right? Good. But now, what would you say about my calculator? Is it working or is it broken? Is it working or broken, Adriana? Why is it broken? Okay, the way she said it could not have been any better. It gave you a different answer than it was before. And so, this is broken. What's another way to say broken? Not functioning. This is not functioning, that is functioning. So now, let's bring back the work we've been doing here. And I did the little experiment over there on the whiteboard on purpose so we had it side by side. So now let's bring back the work we did over here. And I would like you to look at our input-output. This is called X and Y, but this is also called input and output. That's what X's and Y's are, inputs and outputs. So I use those terms over there, input-output, on purpose. So we've got input-output. So the question is this functioning or not? Give me a thumbs up when you see it. I got one person who sees it. I got 3, 4 people who see it. 5 people who see it. 6 people who see it. If you don't see it, don't put your thumb up, because I'll call on you to explain. Okay. You still don't see it. That's okay. It's part of my job to help you see it, so I'm going to give you a hint. Look at that right there. And look at what we did over there on the whiteboard. Give me a thumbs up when you see it. A few more people. Good. A few more people. It's okay if you don't see it. Put your thumbs down. It's part of my job to help you see it. So over here, we did a little experiment. If we have 2 different expressions that get the same result, that's a function. But if we have an expression that gets us 2 different results, that's not functioning, that's broken. What do you see that happened with the 3? What happened with the 3, Aspen? Yeah, it's paired with two different numbers. This right here and this right here tells you that this is broken. If you input a number, you should output the same number every time. That's what a working machine would do. That goes for all machines. Think of your cell phone. You pull out your cell phone and you want to punch in your friend's phone number to text them. If you push the 3, wouldn't you expect a 3 to pop up? And what would you say if you pushed a 3 and a 9 popped up? You would say your cell phone was broken. So machines work because they do the same thing every time. And so that's what is meant by a function. Okay? So this is okay, this is not. And that's what is meant. So let's now actually answer the question. So now you can pick your pencil back up. We're asked to identify the domain. The domain we can list from smallest to biggest. This is discrete, so 3, 4, 5. The range smallest to biggest, -2, -1, 0, and 1. And then we need to say whether it's a function or not, and we already determined that this is not a function. Not a function. And the reason is that one of my inputs had more than one output. The machine's broken. Does anyone have any questions about that? So let's look at another scenario. 3b. You don't have to write the instructions again, but we need the mapping diagram. So again, example 3b, you don't need to write the instructions again, but we need the mapping diagram. And we're asked for the domain, the range, and whether or not it's a function. This is another discrete situation. We're given a set of ordered pairs. The domain, excuse me for a moment. So, I apologize. So the domain is already listed for us in the mapping diagram. List them from smallest to biggest, so make sure you start with the -8, -4, 4, 5. And then the range is simple, 1 and 2. But now we need to determine whether or not this is a function. And so now use our example over here. The only time it's not a function is if we have an input that gives us different outputs. Every other situation is functional. Does this have a case where we have an input that has more than one output? We don't. You're allowed to have two different numbers get you the same output, because there's two different expressions that equal 10 over here. So you can have two different expressions that lead to 2. So this is a function. And so you just simply write function. Any questions about that? So, I would like you to put your pencils down for a moment. The next and last example is just to demonstrate one idea. If you are given a graph, if you're given a graph and asked to determine whether it's a function, this says tell whether the relation is a function. There's a simple way to do it. Does anyone know how to do it? Some of you should have learned it in 6th or 7th grade. Gary?
I just forgot what it says.
Okay, that's fair. It's okay. There's something called the vertical line test, and you can actually use your pencil to do it. And here's what you do. You take your pencil, and you drag your pencil across the graph. So if I just go like this, if at any point my pencil goes over 2 different points, then it's not a function. It's going across a point here and down here. It's not a function. If the pencil passes through 2 points at the same time, it's not a function. Let me show you an alternate, because this one's not a function. Let me show you back here. Here. So if I drag this across here, how many points is it touching right now? 1, 1, 1, 1, 1. So this is a function. No matter what, the pencil is touching 1 point. But what about this one? If I drag it across here, how many points is it touching right now?
2.
1 up there and 1 down there. That's not a function.
Oh.
What about right now? 1 there and 1 there. It's not a function. So if it's called the vertical line test, and so that's a simple way to tell. Yes.
On the other one,
Mhm.
how is it a function? Because it has 2 of the horizontal lines. And it would be
Those horizontal lines are not part of the graph. The graph is this black line right here.
Oh, okay, now I see.
These 2 dotted lines are things we added in. That's not part of the graph. The graph is just the dark line. Okay? So, any questions about functions? Checkpoint number 3. Give the domain and range and tell whether it's a function. We've got 1 minute. It's okay, 1 minute wasn't enough. Take 1 more minute, no big deal. get to domain and range in a moment, but let's address the idea of function. Give me a thumbs up if you think it is a function. Some people think it is, some people do not think it is. Good. Put your thumbs down. Here is the domain. Here is the range. And it is a function because each domain value is paired with exactly one range value. Don't worry about that explanation. So it is a function. If you made a mapping diagram like I had encouraged you to do, you would have seen it right away. Any comments or questions on checkpoint number 3? Okay. Draw a line across your paper to denote that we are done with today's lesson and we are moving to the homework part. And your homework is on page 127, you're doing numbers 1 through 5. On page 128, you're doing numbers 1 through 6. Please write down that that's 24 questions. I know that it adds up to 11, but I'm going to show you in a moment why it's 24. Trust me, the more that we count it as, the better off you are. So all I'm doing is helping you. And you will have a quiz next week. On 3-1 to 3-3. And so here's why it's 24 questions. Make sure you watch carefully because if you mess this up, you're going to totally mess up your grade. Here is the page from the book. And so look at number 1. How many things are you asked to do in number 1? 3 different things. You are going to grade them separately. So on my answer sheet that will be online later, there will be 3 different answers for number 1. If you get this part right, mark it right. You get this wrong, mark it wrong. You get this right, mark it right. That's 2 out of 3. Then we'll do the same thing for number 2. Get it right, get it right, get it right. But now, we're not done yet, so make sure you look up here because the next part looks different than that. Now, for question number 3, it's got 4 parts. So this is how it's going. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then there are 6 questions on the back. Any questions on how to grade it? So this would be graded like this. Any questions about that? Okay.